All right. We are Dakotah Lambert, John Rawski, and Jeffrey Heinz from Stony Brook University. And in keeping with the theme of this workshop on poverty of the stimulus and phonology, we'll discuss how learners overcome the poverty of the stimulus using structure and parameters. All right, so sort of an overview of the talk. We're interested in this problem because phonological induction is successful. And even more surprisingly, phonological induction is successful despite this problem of poverty of the stimulus. And for an overview of this, we recommend you read Lisa Pearl's recent manuscript on PovStim. In particular, poverty of the stimulus means that the input is sparse, it's underdetermined, and it's if distributed. And additionally, there is a lack of invariance in the signal. Okay. A second kind of uncontroversial fact is that successful learning requires a restricted hypothesis space or class. Okay. So we might ask ourselves, what are the structural conditions on this restricted space? What does it mean to be a restricted hypothesis space or class, and what is necessary and sufficient for learning both in phonology and elsewhere? Okay, so a necessary condition for phonology is that this space has to be regular, that phonological induction takes as its hypothesis class the regular class of languages. Okay, so this was a result that's been shown, for example, by Kaplan and Kay. But it's necessary, but it's not enough. We need something a little bit stronger. So to go for necessary and sufficient, the hypothesis space or class has posited to be in the subregular region, or the subclasses of the regular languages. And this is shown by Heinz in many papers, and for a recent overview, see Heinz 2018. The second question we might ask is, why does it look that way? So if we have these structural conditions, where do those structural conditions come from, right? So the answer that Heinz 2010 gave was that they emerge from learning parameters, right? That the hypothesis space of the class is itself determined by learning considerations, and that the typology of natural language phonology is a result of the restrictions put on the style of learning that the learner entertains, okay? So today we're going to generalize this by discussing a typology of mental representations and a typology of learning algorithms. These are the learning parameters that we're considering. The type of structure that you're looking at, and the type of learning algorithm that works over these structures. And our hypothesis is going to be that learners entertain the simplest of these, and so we'll demonstrate what that means. And today we're just going to show this via phonotactics, okay? All right, so this is a part of a general program to understand what cognitive complexity is from first principles, okay? So the question that you ask here is, what kinds of distinctions does a cognitive mechanism need to be sensitive to in order to classify forms with respect to a pattern, right? So when you're reasoning about patterns, you can decompose this into the following questions, right? You need to know what objects or entities or things you're reasoning about, okay? And second, you need to know what relationships between them you're reasoning with, okay? So to formalize these two questions a little bit more, we start with the first one and ask, what are the structures that learners are entertaining when they're inferring information from the data, okay? So what structures are they building, okay? So to formalize this, we're gonna describe this using finite model theory, okay? For those of you who are familiar with model theory and semantics, this is quite similar, but it's now applied to structures rather than the sort of semantic notions that it's usually applied to, okay? So the model in finite model theory of a word, let's say a phonological word, is a representation of it, okay? A model of a word is a representation of that word. A relational model contains two parts, right? So the representation is described in two parts. First is a domain, right, which is a finite set of elements. And then there are relations over those domain elements. Okay, so that makes a relational model. Two important facts are that every word has a model. That's a nice condition. And second, that different words have different models. Okay, this is a very general perspective on structures, because it says that your relational elements, the relations over this domain, describe structural properties of that representation. So this allows you to be very general. You can create models for strings, you can create models for trees, models for autosegmental graphs, et cetera, right? Whatever the type of structure is, the type of structural information that you're trying to describe can be done using relational models, okay? So these models are structures, right? The representations the learners entertain are structural. And if we want to talk about substructures or subparts of these models, right? We're going to give those a special name and call them factors, okay? They're the factors that make up a particular structure, okay? And because this is still a structural notion, we're going to describe a particular parameter. We're going to talk about the width or the size of a factor, like how much of a substructure it is, okay? And so we're going to parameterize this with a number k and call them k factors, okay? So here's an example. Here's one model that we might think of for a word. Let's take a word like sa-sa-sha, okay? Here's one particular representation of it called the precedence model, okay? In the precedence model, we have a domain D, right? It has 6 elements, okay? 1, 2, 3, 4, 5, 6. Okay? Those elements are ordered with respect to each other, and they're ordered using the precedence relation, or the less than relation. This relation allows us to immediately describe the information that element 1 precedes element 2, 1 precedes 3, 1 precedes 4, 1 precedes 5, 1, etc. 1 precedes 6. Okay? Also that 2 precedes 4, 2 precedes 6, and 3 precedes 5, etc., etc., etc. Okay? We also have what are called labeling relations, which define properties of these particular nodes. So for example, we know that elements 1 and 3 have the label S, element 5 has the label sh, elements 2 and 6 have the property of being a vowel with a high tone, and element 4 has the property of being a vowel with a low tone. Okay? So with the information that's described in this model, right, we can extract substructures of this model in the following way. We pick domain elements, we can pick a set of them, and then we describe all of the relational content that holds between them, okay? So here's a factor, all right, of size 3. So we're going to call it a 3 factor, okay? You can also think, if you're familiar with the term from strings, this is a subsequence of size 3, okay? So what this tells us is we have a node with the property of an ah with a high tone. It precedes this node with the property of a vowel with a low tone, and it has the transitive property that we know that because this one precedes this one, we know that the first guy here precedes the third guy as well, okay? So this is a substructure of size 3. We can think of other substructures of other sizes as well, but this is one example, okay? What other models of words are there? Well, let's take the transitive reduct of this model, which we might call the successor model, or the model that encodes immediate adjacency. Note that everything is the same in this model, same size of the domain, same labeling relations, but now rather than looking at general precedence, we're just looking at which items sit in immediate adjacency with respect to each other, right? So what can we immediately infer from this model? We know that, for example, this precedes this s, and this precedes this but we cannot immediately infer that this precedes this right? That the high tone vowel precedes the low tone vowel. We cannot immediately infer that, right? We have to do some transitive work. There has to be some additional work that goes beyond that, okay? But we can still extract factors from it. We can extract subfactors. Here's a 3 factor again, but notice that this factor only encodes whether the element is within immediate adjacency with respect to the others or not, okay? So this is a 3 factor over the successor model, okay? This is very similar to a trigram, okay? So a k factor in this sense is basically just a k-gram, okay, when interpreted over strings. Okay, right? So we might not want to talk just about whether any element is next to or immediately adjacent to another one. We might want to ignore elements with some property. So for example, say we only want to talk about the sibilants, right? I only care whether certain sibilants are precede each other or not, right? Well, for this, we can relativize this sort of immediate adjacency to only apply to properties which share a certain type of labeling relation, right? So here is immediate adjacency, or successor, with respect to particular segments. Here are the 2 sibilants, sa and sha, okay? So this model, when we extract a factor, we still get a 3 factor out, and it's still using the successor relation, but it's parameterized additionally with respect to these alphabet symbols. So now we know that the sa precedes the sa, even though they are discontinuous, right? We just don't care about the stuff that's not on the tier, okay? So this directly representationally encodes the notion of a tier. In this case, we have a sibilant tier. This is the sibilant tier. It allows us to say this, sa is an element, is a sequence, or in fact a substring on this sibilant tier, right? So there's a notion of locality that's relativized with respect to certain phonological content, okay? If we aren't happy with just having one tier, we can consider as many tiers as we want. And here, in fact, we have another model called the multi-tier successor model, okay? Just as the name implies, there are no multiple tier successor relations. So we might want to consider the sibilant tier, right? And whether, and it extracts, say, a 3 factor on the sibilant tier, Or we might want to consider the vowel or tone vowel tier and extract a 3-factor on this tier. So here we can make statements like, do we see, you know, a sa followed by a sa somewhere? And do we see a high tone followed by a low tone followed by a high tone, right? So we might want to make statements about tone plateauing in addition to, say, statements about sibilant harmony, right? And we do that by evaluating these substructures as we parameterize them with respect to the particular model, okay? Right, so there are many different types of models you can consider. We're going to work with these four for today. And these 4 model signatures, this is one parameter of our overall argument. The second parameter has to do with how the learner collects the factors, okay? The learner collects factors of a certain type, but how it does so describes the typology of online learning algorithms, okay? Online meaning that the learner gets a form and then they immediately perform inference on it. They don't need a batch learned algorithm, okay? So generalizing string extension learning from Heinz 2010, one can use the factors to infer grammars from the data, okay? And you do this, learner can do this in 4 different ways, okay? The first way is to collect all of the k factors, right? So you give a learner a parameter k, and it just says, I see a word, I collect all the k factors. But the first learner ignores words longer than k, okay, right? So if k is 2, if you only want 2 factors, you're only going to consider words of up to length 2, and anything longer it doesn't care about, right? The second algorithm says, well, I actually do care about words longer than k. I care about any word, so I'm going to say, if I get a word, I'm going to collect any k factors, okay? And so I'm just going to collect all the different factors that are present. A third learner makes more distinctions and says, I'm going to collect sets of k factors. Okay, so not only am I collecting any k factors, but I'm collecting all the different sets of them. Okay, learner 4 additionally makes even more distinctions and says, I'm going to collect multi-sets of k factors. All right, so I'm going to count the amount of times that something is in these sets. And additionally, we're going to parameterize this learner with some constant t, which says that we're saturating it. So the learner gets to count up to some point t. Okay, we're just going to give it an upper bound here. All right, so let's do an example. So let's say our learner sees the word AAAAB. Okay, very nice binary alphabet. Okay, the learner sees AAAAB, and let's say the learner is biased in that it has the precedence model. Okay, and let's say the learner is further biased by considering a k and t that are equal to 2. Okay, so the width of the grammar is of size 2. Right, so what do the different algorithms do? Well, algorithm 1, right, because this word is greater than k, right, it doesn't do anything, right? It just returns the empty grammar, right? It just doesn't consider it. The second algorithm takes all of the factors that it sees and then adds them to a set and doesn't care how often it saw them, right? So even though it saw AA as a subfactor more than once, it just adds it to the set, okay? Algorithm 3 works kind of similarly, but it structures these into a set. So it has the set A, B, and then the grammar is the set of that set. Okay, algorithm 4 now does count the items in the set and now says, okay, well, I did have this set where I see AA twice, and I have this set where I saw AB once, and so it arrives at the following grammar. So you can see that by varying the choice of the algorithm, the learner over these various model signatures uses the way that it extracts the factors in order to make more distinctions between the elements in the grammar. Okay, so these learners are, in a sense, more complex with respect to each other. Okay, so they increase in complexity. All right, so now we have a typology of learning algorithms and a typology of representations. So what happens when you put them together, right? What happens when you use an algorithm on a type of model signature? Well, these are exactly the parameters that derive the subregular hierarchy. Okay, so when you take the typology of learning algorithms represented on the vertical axis here, and the typology of structural representations, the precedence, successor, tier successor, and multi-tier successor on the horizontal axis, the combinations that you get give you exactly the subregular hierarchy. Okay, and so you get this sort of grid of 16, well, actually it's 15 different algorithms, right? It's notable, a notable quirk is that over the precedence relation, algorithms 3 and 4 don't actually make any difference with respect to the distinctions, but this is a minor quirk, right? When you interpret these 4 algorithms as being, as making more distinctions, you'll see that the difficulty of learning increases as you go up the vertical axis, okay, right? Namely that, for example, over the successor model, it's more difficult to learn the strictly local patterns than it is to learn the complement strictly local patterns. It's more difficult to learn the locally testable languages than it is to learn strictly local, and so on and so forth. Okay, right, so here we get a typology here and a typology here. And so we have 15 different classes that the learners can consider patterns in, right? And this is merely just from considering the different ways that the learner can combine structures and the different types of structures that the learner can have. All right, so 15 different hypothesis classes. Why might a learner not prefer all of them? Okay, how can we restrict this class even further? Well, let's ask how these algorithms behave with respect to each other. Okay, so one way to ask how an algorithm behaves is to say, well, how big is it? How much space do I need to store the grammar? Okay, so let's see how the algorithms store the grammar and how this size increases. And it turns out there's quite a big difference. Okay, all of them kind of require a lot of space to store the grammar, but there's a pretty big difference between the grammars that only need to collect the factors and the grammars that need to collect sets or saturating multi-sets of factors. Okay. So this difference is pretty pronounced. In fact, a learner that needs to entertain, the learner that uses algorithms 3 or 4, right, namely the learner that needs sets or saturating multi-sets, requires exponentially more space to store the grammar than a learner that only considers factors. So this is kind of noticeable if you look at, say, the learner entertaining factors, collecting factors of size 4 or 5, right? Already when you're just having, say, factors of size 4 or 5, the learner that learns via algorithm 3 requires more space to store the grammar than there are synapses, than there are average number of synapses in a human brain, okay? All right, so in any notion of biological plausibility, that is just out, all right? All right, so let's see what happens to the typology of hypothesis classes when we take into account the space requirements. All right, so now if we look at it, it bisects the line. If we look at subregularity as a property emerging from these typologies, and we additionally add the constraint of space, we see that we can take this line and just bisect this guy right down the middle, right? So now we've reduced our hypothesis space from 15 classes to 8 classes. Okay, so now we have a learner that's restricted just to these guys: the piecewise, strictly local, tier-based strictly local, and the multi-tier based strictly local, and their complements. All right. Now, are there any other ways we might restrict a learner? It's a nice question to ask. Well, an additional way to ask how the learner behaves is to say, well, how fast is it, right? How efficient is it in time, right? What's the upper bound on the time limit that these learners can entertain, right? And let's go as strict as possible, right? And let's just say, okay, we want a learner that's linear time, all right? So what learners are restricted to linear time and are cheap in space and are subregular, right? When we do that, we restrict the hypothesis class even further, right? And we say that the learners that can only entertain subregular classes and they're cheap in space and they're linear time, right, are exactly the strictly piecewise, strictly local, tier-based strictly local classes and their complements. Okay? All right. So this is a pretty restricted learner, and it's also quite easy to test these predictions, right? Because now you can ask yourself, right, so here are the types of patterns that these learners can learn, right? We know what these classes look like. We know what types of patterns should sit inside them. How can learners learn them? Is this what happens? Is a learner that is exactly restricted to this type of simplicity behaving in this way, right? So how would we test this? Right, how do the predictions match the evidence? Well, okay, there are many ways that we could look at this. Let's start with typology, right? We can just say, if we see a pattern in the world, obviously it was successfully learned. So we can take that, say, as evidence that the hypothesis class of a learner has to include classes of this or patterns of this type, right? So in the typology, we see many examples of strictly local patterns and strictly piecewise and TSL and MTSL patterns, right? When we look at the other classes, the classes that sit outside these guys, virtually none. Okay, there are some controversial examples, but virtually none. Okay. Additionally, when we look at the multi-tier strictly local class, Aksionova and Deschmuk had shown that the interactions between the tiers, when you consider multiple tiers, are restricted. That means when you add items onto a tier, you can't just combine these tiers willy-nilly, right? They suggest that this is a learning bias or a learnability bias. And we're going to go even further and suggest that this is a bias towards the linear time classes. right? So if a learner is allowed to be MTSL, maybe it'll consider it, but it's only going to consider the first one, which tells us that it's really not inhabiting that class. It's in fact inhibiting, it's really going to sit towards the linear time classes and maybe consider some others, right? All right. So maybe the typology isn't convincing to you. Maybe you'd also like some evidence from carefully constructed experiments in a laboratory. So there are many results which support this. Here are several of them. A paper from Lejeune Lai from 2015, McMullen and Hansen from 2019, and Finley 2009. And all these sort of confirm the same prediction, that learners are biased towards strictly local and strictly piecewise and TSL patterns in artificial grammar and artificial language learning experiments, even when they're allowed very plausible alternatives, okay? So when learners are confronted with hypothesis classes which could include these, they are instead biased towards these particular patterns. All right, so now we've arrived at sort of a trifecta of results, right? We have the results purely from mathematical reasoning, backed up by data from the typology, and as well confirmed by results, carefully constructed results in laboratory learning. And this trifecta pushes us towards the conclusion that learners efficiently overcome impoverished data through biases towards simple representations and learning parameters. Thank you.